Yeah, so while you're pulling up the video, just a very super brief introduction. Uh, OpenAI has made it clear that their new image generation uses an autoregressive process. Now, of course, they're not giving away any of the details, but since they announced that they're using something autoregressive, they're not using diffusion. Um, then a lot of people started asking uh, questions and taking more interest in this autoregressive image generation paper that that was at NeurIPS, and people were kind of talking about at the beginning of the year. So now there's like renewed interest in this paper. So that's the reason why we're going to kind of take some time here to talk about this and how it's different from language um, autoregressive generation, and also how it's different from, of course, other uh, video. I keep saying video image generation. Um, I do video stuff all day at work. Image generation stuff such as diffusion and whatnot.
Discussion. It won one of the two best paper awards at NeurIPS. So this paper is VAR. It's Visual Autoregressive Modeling. And I like this paper in particular because people have been taking transformers and sort of copying the success of LLMs and using transformers for lots and lots of other different fields. AlphaFold uses transformers, a billion things use transformers, but for image generation, not for classification. For image generation, the results have been somewhat lukewarm so far. And so this paper tries to do something different. So just to give a quick high-level overview, what the authors do here is they want to generate the power of LLMs. And what people had been doing is, in an LLM, you have an input sequence. And so maybe they would try something like a raster scan, where you break the image into patches, and then you just kind of go across the top from left to right, and then you go to the second row from left to right, and so on. And it works, but there's something kind of unnatural about that because a pixel in the middle of this dead center of the image will depend on the pixels above it, but not at all on the pixels below it, which seems a little bit weird, right? And within the same row, it depends on the pixel to its left, but not at all the pixel on its right. So there's just something about like our natural understanding of images and the relationships between images, between pixels. So there's going to be tight relationships for local pixels that are very close to you in all directions. And then certain general relationships that where, like, if you have a picture of a dog, then the color of the coat is going to have a certain relationship, even for pixels that are very far away, and possibly in any direction. So since that's sort of an unnatural thing, there's been discussion about, well, how can we do something different? And this is a paper that seems to have found a successful recipe. So what VAR does is it says that going from low resolution to high resolution is a natural sequence that has a clear ordering. Okay, just like language, English, we read left to right, has a very clear ordering. This is the clear ordering from low res to high res. And it has this nice property that a medium resolution image will depend on, sorry, one second, guys. Just gonna pull this up one sec so that I can. All right. Hopefully we can kind of manage the audio. So if you say that a medium resolution image depends on a low resolution image, but that whole image, then once again, you've restored this property where it depends on the properties, not just of pixels in a certain direction, but all the possible pixels in that lower resolution image. And so you can imagine, like, if we have a dog just sitting on the grass, maybe a very low resolution image, we can see the color of the coat and it's kind of blocky, and we can see the green of the grass and the blue of the sky. That's all we're really getting. But that's good high level information that tells us this is a, let's say it's a German Shepherd, a brown and black something in a green background with a blue sky, right? And then we can, as we get higher and higher resolution, we start to see things. And so then once you're getting close to the final resolution, you may say, there's things I know about, like whatever, the paw, the face. If one eye is a certain color, then almost all the time the other eyes can be the same color, those kinds of details. So this seems like a really nice natural sequence. But as we'll see, like, okay, that as a high level brushstroke, that's fine. But then how do you actually do this? How do you pull this off? So when we go through this, we're going to look at a number of different concepts. These are older concepts that are used in order to build this. So we're going to talk about, again, very briefly for the purpose of just this high level overview, but we're going to use variational autoencoders. And tokenization happens a lot in transformer-based image models. But for things like patch tokenization that VIT uses, it's basically projecting into a continuous space. So you may have a 16 by 16 patch and you project it to a whatever length 128 vector of floats. There's infinitely many possible length 128 encodings because it's just a floating point. So what we really want in order to use our LLM-like transformer for prediction, we need a discrete vocabulary, just like language models may have a vocabulary of 30,000 tokens or 50,000 tokens or something like that. So in addition to regular autoencoder, VAE autoencoder technology, we're also going to use vector quantization. So if you're familiar with VQ-VAE, and technically there's a VQ-GAN addition where they just add an extra loss to make the images look a little better. So we're going to use VQ-VAE. We're going to use a very vanilla LLM. It's basically a clone of GPT-2. And on purpose, and this is one of the things I think that was really strong about this paper, they use GPT-2 mostly, almost completely as is. And so what they said is, we don't want people to say, oh, well, you had really good results because you used some fancy new LLM, you used a better activation function, you used a better this, a better that. They're like, no, we used ancient technology and we still were able to beat these other models. And then what we're going to see is that when you're going from low res to high res images, these images are not going to be just one token anymore. And that's another thing that I love about this paper. I think this is an underexplored area with transformers and LLMs, in that language, we've just been predicting one token at a time. And now what they want to do is they want to predict an entire image. They want to predict multiple tokens at once. How exactly do you do that? Like there's not a super obvious precedent for how you do this. It's not like, it doesn't take like rocket science, but it just requires a little bit something. So we're going to need to figure out how to do that, and we're going to have some special masking to get that right. So that's just a high level overview of the concepts. So let's just go one layer deeper. Okay. So as I talked about, for LLMs, we have this natural ordering to language. Okay. Technically, doesn't matter whether on the paper you do left to right or right to left. We think of language as just this one-dimensional linear sequence, and it has a clear order. And so we model this. Theoretically, you could say, okay, somebody asked me a question, and I'm going to output 16 tokens. Let me just predict all the 16 tokens at once, and that would be this massive joint probability problem. And so what we do is we decompose it, where we say we're just going to have the next token be conditional on all the tokens that we've seen so far. Before I ever saw this work, might scratch my head and say, is that really enough? Is that really just that little conditional probability, one token at a time? Is that sufficient? Turns out that GPT-4 works pretty well, right? So to copy that, you can see here a simple, a smaller example where there's a picture of a parrot, and we've just broken it up into 9 patches, and you kind of go top row, left to right, middle row, bottom row, like that. So as I said, this is a little bit unintuitive because, for example, patch 5 depends on patch 4 and patch 2 that are right next to it, but it does not depend on patch 6 and 8 that are also right next to it. Okay. This also has a problem that if you have a relatively big image and you have relatively small patches, you end up with a lot of patches. And when you have a lot of patches, two things happens. One, it takes a lot of transformer inference steps in order to output all of these patches. The other thing is, as your sequence gets long, as people know, with this quadratic cost, then the cost of doing all of this goes up. So really just trying to figure out how to do this, and it hasn't worked really well in papers and models so far. So what do we do instead? So we're going to have this, as I said in the overview, we're going to have this spectrum from low res to high res images. Okay. And it's best at this point of the game if you just think of images as an image. Don't worry about what's the data representation. At this high level, it's fairly intuitive that, like, oh yeah, I can see, again, we have our parrot, that, like, you know, maybe this third one over here, you're starting to see some of the pattern. And so if I asked you, you know, is the parrot facing to the right or is the parrot facing to the left? You probably could look at this thing that's labeled R3 and say, yeah, I'm going to guess that's facing to my right because the beak's black and I can see there are these black pixels over here on the right. Right. And then definitely R4, you know, you're starting to really, if I asked you, what is that? You know, you can say it's a parrot, but there's going to be fine details about the feathers and other things that still haven't been resolved. And as I was saying, there could be some global dependencies where, you know, part of the parrot that's blue, maybe that, I think that's maybe the wing, you know, has general global dependencies on other parts of the wing that are also blue. And so, by having this high-res image informed by this lower-res image, you can sort of communicate information up. So, in one sense, I feel like you can do parallels to like diffusion, where the image sort of slowly comes together. The vanilla idea of diffusion, it's a little bit more like you have noise, you have these weird pixels, but you're sort of getting the gist of it. This is actually different in the sense that you literally have something that's blockier, chunkier. There's not necessarily noise with individual little pixels, but rather there's just noise at this scale level. Okay. So hopefully, I'll pause here. Any questions just in terms of this idea of we've found ourselves a one-dimensional natural ordering, and it seems to have the right inductive biases for images in terms of how we can say the conditional probability of a higher resolution image on all of its priors, all the smaller images, kind of makes sense.
I have a question.
Yeah.
So what is the ultimate function of having this autoregressive process at the end of the day?
Yeah. So so the question is, what is the purpose of having this autoregressive process? So with language, we've seen that at least what I thought might not be a strong enough prior, a strong enough conditional probability, is actually able to generate amazingly complex sentences and solve word problems and do things, even though it's a really kind of a weak, conditional relationship, right? So the idea is, if you have the right conditional relationship with images, maybe you can solve really complex image problems. And in particular, I think that one of the ideas is that you build something and it kind of works and you're like, yay. And then you start scaling it up and you make it bigger and bigger and bigger. And ultimately, what we see in a lot of models, there's a slide at the end that has the curves, that the performance just gets better and then it just hits a wall. Your performance just doesn't continue to get any better. The superpower of the transformer GPT architecture is that it continues to scale as you get bigger and bigger. So when we talk about those power law scaling laws, okay, with the advances in computing power, people have gone back and built giant versions of older architectures. And so it turns out that, like, you can actually get an LSTM model that's just as good as GPT-2. which at the time we would, at GPT-2, we wouldn't have thought you could do that. But now we have enough compute and whatever, we can just crank away and we can actually build it. But the thing is, if you just keep making that LSTM bigger and bigger, it'll plateau. So the same thing happened with Mamba. 1 year ago, Mamba came out and we're like, wow, at like the 1 billion size, it's like just as good as an LLM. I haven't seen specific results, but I'm just sort of inferring from the absence of anybody building, Mamba-based GPT-4 that it doesn't work. People tried scaling it up and ultimately it plateaus. So if you have any kind of inefficiency in your architecture, in your sort of, prior to prediction conditional probability, you're going to hit a glass ceiling. Okay. And so the idea is that maybe if this is a very true, no inefficiency, no garbage, no missing stuff, so like the truth, the whole truth, nothing but the truth, right? If it's got that kind of relationship, then we will actually see these scaling laws, and that if you power it up, then given a hard enough image problem, all you need to do is grow your data and grow your model size. Those are not necessarily trivial, but nevertheless, you won't hit a wall.
So this is a means to overcome that plateau.
Yes. So right now we have things, and that, yes, also this might be a little faster and this might be a little whatever, but that's the main thing, is that you want an architecture. And so ultimately, if you get all of these things, maybe you can then work on being sample efficient in training, and you can work on being fast in generation. But ultimately, you want something that sort of learns well to begin with.
We're just kind of following up on that. Can you clarify a little bit of what you mean is what would you consider as inefficiencies from the architecture?
So what are inefficiencies? So for example, for raster scan, this idea that a patch cannot depend on a patch below it. You could imagine, I could come up with a intentional counterexample where all the information you need is below the pixel. And then you're going to make a really terrible prediction at that pixel because you just haven't seen the thing that you needed yet, right? Yeah, maybe that only comes up X% of the time in images, but fundamentally, that's the phenomenon that at a local and a global scale, you're not collecting all the priors you could be in the right way.
One question. So you mentioned VQ-VAEs. So is it here that the similarities are, obviously you also mentioned the concept of we're going to have like a vector space and it can be quantized and we're only going to use the vocabulary to represent the Latin space at the end. So do we also do like the similarities with VQ-VAE is that we start with the denominated space and then we build up decoding back into the image and then that's loss function?
So the questions about VQ-VAE and the latent space, let me actually get to that in the next couple of slides. So that's the perfect question to lead to. Yeah.
After not really precedent for looking at the pixel below, etc. In voxel, so like ray tracing for voxel, there's some people ray planing where you basically say, hey, let's create a sphere or a box of radius r. This is the same color. There's nothing changing for that distance. So that's something that may be applicable to this.
Yeah. So I'm not going to be able to reproduce your comment in full, but in terms of like ray tracing, I'm not a computer graphics person. I don't know everything. The issue though is that if I said I've trained this model on ImageNet and it knows cats and dogs and things, generate a picture of a dog. Okay, you can't draw a box around a pixel to inform it because you don't have any of the pixels below it yet. You just have a blank slate. You only have the pixels above you and on your row to your left. So you can conceptually say, yes, just be informed by everything around you, but I only have half of the things around me. That's the fundamental problem. And so it's a chicken and egg problem because you're like, well, then just generate the pixels below you. Well, how do I generate the pixels below me? Because they don't have the ones below them yet. And there have been people who said like, oh, instead of doing raster order, we'll do a spiral, we'll do a space filling curve. But it's always the case that when you have a sequential ordering, there are pixels that you should be informed by that don't exist yet. And this idea of going low res to high res, you don't have that problem. You still have to decide, is low res to high res a good idea? But every pixel in resolution 4 has access to every pixel in resolution 3. How the model still needs to learn how much to weigh the local versus the global dependencies. You shouldn't say this pixel on the dog's paw is highly dependent on the sky, you know? So you need to learn those patterns, but at least you have the ability to have all the data that you want to depend on at your disposal and obviously logically ignore the things that you want to ignore. All right, so let's keep going for a second here. Sorry, actually there was a
Let's go ahead and stop on our end, I guess, since we had Ted live. Does anybody have any questions on that for Ted?
This is going to get a little confusing. When, who's stopping when, what?
Yeah. Well, I'll come on then. That wasn't in San Diego. So, anybody have anything for Ted, since we have him here and we can't let him just fall asleep watching himself.
I had a couple questions. So one of the questions was, are the channels in each of these lower resolution quote unquote images, are they color channels, or is there kind of a higher dimensional latent space in the lower resolution?
Yeah, that's a great question. So one thing I didn't make clear is that the model itself is working in the latent space. So it's going to be working in lower resolutions in the latent space. However, in terms of like the final reconstruction, that's always going to, of course, be back into a pixel space that we can see. But the internal representation that the transformer, that the GPT-2-like model is going to see, is going to be latent space embeddings.
Okay. And then is the transformation, when you're training this, do they only train on the final image, or is there anything that happens at lower resolutions?
We'll get to it. Yes, they have to build something special that can handle multiple resolutions. Yep.
Okay, and so the transformation from latent to color, does that happen then at all the levels also?
Yeah, I mean, basically, they're going to build a VQ-VAE. Okay, so this is an autoencoder. So it's going to have an encoder half and a decoder half. Yeah. And so basically, once you've made your predictions, you feed it to the decoder and it spits out pixels.
Okay. Okay. And then lastly, in your comments and the first time, I think you said something that kind of, it's almost amazing that the original, what was it, just VT, the visual transformer, the way that it would even work when you just did kind of a linear set of tokens.
Yeah, no. I was actually saying that like GPT-2, GPT-3, that they work.
Oh, on language. Okay.
On language. I don't know that former me would have bet money that if you just scaled up, that this thing would be able to solve international math Olympiad problems.
Oh, okay.
You know.
Okay. So then I'll decouple the question. That the original visual transformers, I believe, just like encoded, they did some sort of tiles that they would do an encoding on each of the tiles and then selected the tiles in some sort of raster type style, right?
Yeah, the original VIT paper, I think all they did with it was classification. So it was not a generative model. So then there has to be some other thing you layer in order to then ultimately say, I'm going to build a generative model. And that's why you need like a VAE or something else that allows you to sample.
Gotcha. Okay. Okay. I missed that nuance. Okay. Thank you.
Yep. Any other questions? Anybody else? All right. So far, we've only seen the high-level idea. We have not talked about how they implement any of this. So now we're actually going to go into some of the components and how do you actually implement this idea of going from low to high res.
Question in the chat. Yeah, so So I'm gonna explain a little bit more. So hopefully that'll answer the first question. And then yeah, you can come up with different orderings, but you still have this fundamental problem that some pixels don't exist yet, and that's what we're trying to find a better. I'll call it a better inductive bias. So the thing is, how are we going to implement this idea of going from low to high res images? I said for now, to start with, let's just ignore the idea of how do we represent. But now, okay, now that we've done that and talked about is this a good inductive bias? Now let's actually get down into it, and it's kind of hard. I mean, when you get to the later resolutions, you're talking about a whole lot of pixels, and are we going to somehow jam that into one token for our LLM? That doesn't really seem right. So we're going to want to do a couple things, and one of the things we're going to need to do is we're going to need to reduce the dimensionality. We cannot work in pixel space, okay? This is a pretty common thing, even like diffusion, you know, the move from pixel-based diffusion to latent diffusion. So we'll talk a little bit about autoencoders here. And again, this is just going to skim the surface so you can do further reading. But a regular simple autoencoder, you know, you can imagine you just have some fully connected layers. Gradually, they get smaller and smaller, and you reach a bottleneck in the middle that is your compressed embedding. And so this is a very common technique in order to get embeddings, but this is a deterministic process. So if I say, here's a sample image of Lassie, okay, and I get this embedding Z, and I say, okay, now go generate me some images. All I'm going to do is get Lassie over and over and over and over again. There's no way to get Lassie in a different pose. There's no way to get another collie. You just get this one thing. So we need something that's not deterministic. And for that, that's where the variational autoencoder comes in. So instead of having just a fixed bottleneck, we're now going to have a probability distribution that it compresses it to. And so here you can see it expressed as a multi-dimensional Gaussian. So you have a vector length of means and a vector of standard deviations, and I think this is just a diagonal covariance. So there's just a vector instead of a square matrix of standard deviations. Regardless of the details of training and whatnot, the idea though is that I now give it an input, which is a picture of Lassie, and it says, I have this probability distribution centered around what I think this concept is that you're trying to teach me. Now, from that probability distribution, I can sample, and I can generate many different images. If I give it the right input, the right direction, then I can say, okay, look, here's Lassie running, here's Lassie sitting, here's Lassie sleeping, here's, you know, whatever. Okay. And then obviously we can get more and more complex in terms of, you know, make it text conditional or whatever. So variational autoencoders were some of the early image generators. Not going to talk about them too much, but for this paper, we are going to use that concept, but we're going to add another layer to it. And so that's going to be vector quantization. Sometimes when I talk to people about vector quantization, they ask, is this like some very fancy concept? And in my mind, the best way to explain it is it is not. It is just a way of taking your idea of rounding and expanding it to vectors of whatever length. So if I had floating point numbers between 0 and 1, and I said round it to the nearest 100th, you would have 100 buckets. And you would just simply say, for each number, I'm going to assign it to whichever bucket is the closest. There's other ways you can think about rounding, but that's sort of my distance intuition of how you assign floating point numbers to one of these 100 buckets. I'll throw in that you don't have to have 100 uniformly spaced buckets. You could actually have the buckets that are, say, denser around 0.5 and sparser around 0 and 1 if you wanted to, okay? You could learn what are the right 100 buckets that get you the best coverage of your floating point numbers. Let's say they're not uniform random, okay, right? They're distributed some other way. So you could learn that. And then ideally what you would want is roughly the same number of numbers to fall into each of these 100 buckets. So if you just say, fine, I did that. Now how do I do that on a length 8 vector? It's really logically the same process. It's just that your 100 buckets are going to be spread out in 8-dimensional space instead of just linearly. So it's a little harder to draw them, but you just start with 100 buckets and you assign every vector to its closest one. And if you want, you can train them so that the buckets themselves are not uniformly spread out, but rather they get clumped based on where your data is, so that you have roughly the same number of vectors that get assigned to each bucket. So that's my way of saying that I don't think I think it's possible to think of vector quantization as really just multidimensional rounding with learned buckets. It doesn't have to be some really complex concept. So what we can do is in our VAE
Jerry, we have a hand
before
raised.
we had this.
Hey, Jerry?
Yeah,
Oh, it is, okay. I
It
didn't
is.
know if you were, I'd raised my hand. I wasn't sure if you were stopping for that or not, but I just want to clarify. So Ted, it's not quantizing on the dimension, each of the dimensions. It's more quantizing in the subspace. Is that correct?
Yeah, it's doing the entire vector all at once. It's
Right.
not bucketing the first float, bucketing the second float, bucketing the third float. It's saying this entire vector, which bin or bucket am I going to put it in?
Okay.
Okay.
Do
So
you have any insights? Like, how does that work? Like, how do they figure out what's a mechanism figuring out what are good buckets?
yeah, so basically, let's say you let's do 2 dimensions instead of something really complicated, like I said in
Uh,
video 8, right? So you can imagine then like all the directions in 2D is just going to be like in a circle, right? You could have
yeah.
east, north, whatever, right? And super simplistically, uh, um, intuitively, if I just gave you a bucket full of 500 vectors in 2D space, okay,
Mhm.
you could actually just draw them all on the circle or whatever, and you could pretty quickly see like, wow, there's a whole bunch of them that point close to east or whatever, right? I'm going to
Yeah.
need a lot of buckets over there, and there's almost none of them that point west, so I can have like a giant bucket that's like for all the stuff that's between northwest and southwest. Okay.
Yeah.
The way you do it mathematically is you assign everything to the buckets. Okay. And then you reconstruct it. Your decoder basically, if it only knows the bucket number, then it's basically approximating each of your original data points with the center of that bucket. Okay, with sort of like the whatever you want to call it, the centroid, the median, the whatever, right? And so you're going to get a rounding error because of that. Does that make sense? So if you
Yeah.
assign everything to a bucket and then you represent them all as their bucket center, then you're going to get a rounding error. And so what you do is you just do like mean squared error, and so you say that's how much my rounding error is. And then what if I tweak the bucket a little bit? Can I reduce that rounding error? And if you do that, then ultimately, what you wind up with is intuitively what you would want is you have all the buckets more smaller and more densely located near where you have a lot of data points, and the buckets are going to be very large and sparsely populated where you don't have a lot of data points. So the process is just our usual, mean squared error. You can run gradient descent, but
Can I ask?
what you wind up with is, I think, intuitively, if you just looked at it and you tried to divide it, then you'll get the same results that intuitively, if you were just trying to pick buckets, that would give you the same number of data points in each bucket.
Can I ask?
Yeah, Julius.
Why do we need buckets? I mean, why can't we just leave the vectors where they are and let them be a mean and a standard deviation?
So the reason we need buckets is because we want to use a language model. We want to use GPT-2 ultimately to predict our pixels. Okay, and GPT-2 is a discrete model. It has discrete token inputs based on a vocabulary. Okay, so like the actual GPT-2, I don't know, its vocabulary might have been 30,000, something like that. Okay, and so your inputs, you one hot encode them, whatever, but basically it's the integers 1 through 30,000, right? Now, theoretically, you can cheat and you could say, I'm going to just like shove some continuous data into the input of GPT-2 instead of using discrete tokens the way we normally do. But even if you cheat on that side, you can't cheat on the decoder side. On the decoder side, you have a softmax that's predicting one of 30,000 possible buckets. And we need, in order to be able to interpret our predictions, we need to have a discrete distribution. And so that's what the goal of this paper is can we basically turn our image generation problem into exactly the same formulation that GPT-2 was, which is I have 30,000 possible discrete inputs, and I'm going to predict the next token, which is one of 30,000 possible things. Can I actually figure out a way to turn my image problem into that problem?
So why don't we use buckets all the time? Why don't we have them like at every transformer layer at the output of the attention? Why don't we bucketize that? And sorry if I'm just like,
no,
see, I don't know about buckets.
It's a good question. It's
a valid question. I mean, all questions are valid, right? So in this case, the conventional wisdom of what transformers are doing on the inside is that they're representing data as directions in a vector space in a very continuous, dense vector space. And we're allowing them to work continuously until they get to the very end, and then we run that softmax and we get a discrete prediction. If we did any discretization in the middle, we'd be creating more rounding errors. And we would probably be making life harder for the transformer. I can't off the top of my head think of anyone who explicitly published results trying this. Probably somebody did, but my intuition says that by introducing extra rounding errors, you're not really helping things. The reason why we do the discretization here is because we have no choice. At the input and the output boundary, it has to be a discrete distribution. But everywhere else, if it doesn't have to, we're probably better off. The expressive power of a 256-dimensional, like R256, is a lot larger than the expressive power of 30,000 integers, and that's it.
So, Ted, an interesting tie-in from here back to or forward to continuous chain of thought. They didn't send it through a softmax before they send it back into the input. So it may not be the case that we have to quantize it on the input or the output. It could be an embedding space output and feedback.
So I think there's very interesting possibilities. So Julius asked, why between layer 1 and layer 2 do I leave it continuous? Why don't I discretize there? And between 2 and 3, and then up to 23 and 24. Okay, we do discretize between 24 and going back to layer 1. Okay, and so the continuous chain of thought says, what if I don't discretize? Can I take advantage of that higher expressive power? Except, here's the big catch, okay? You can only do this on positions where you're not actually predicting the next token, the next word. So you can let it do this 10 times if it's thinking mode, but as soon as you want it to output the next word, you have to then run the softmax. You have to discretize it.
Well,
so yes,
in the language, and I'll buy that in a language application, because the language is more or less, you need letters on the output eventually, right? But I think it's a reasonable question of, is it necessary if you're dealing in a space that isn't quantized like that? If you're dealing in, maybe signal, maybe, an image space, if you view it as more.
I can't remember specific papers off the top of my head. Maybe if I think about it a little bit. There have been people who built GPT-style transformers, had it predict continuous outputs, and just used mean squared error loss instead of using cross entropy. and none of those have had earth-shattering results.
Oh, interesting.
Okay.
Okay.
So I think when you work in language mode style, like with like with discrete, with cross entropy, what you can do is, depending on your tokenization scheme, you can just apply more and more tokens to represent the information that you want in order to get higher resolution. Okay. So for example, when they're doing AlphaFold, they don't represent the whole protein as one token, right? They do something like one token per amino acid, per whatever.
Yeah.
I forget the term, right?
Yeah.
Okay. And hypothetically, you could even do 4 tokens per residual, whatever.
Sure.
Residue.
Sure. But
right?
it is
you
quantized.
could do 25 tokens per residue, right? When you do continuous, you're kind of saying, I'm going to read that float out as is, and you really have, to a certain extent, forced your hand that you're only going to have 1 token per real number that I'm outputting.
Yeah. Yeah.
Okay. Now,
yeah,
again, there's other games you could play. Let me massage my data and take that one floating point number and somehow spread it over multiple positions or whatever. But that's the best answer I can give in terms of like why do we still use this discrete thing, is because it works really well, right? Like
it's worked well for language for sure. Yeah.
It's like when there is a fundamental unit of meaning, then you want to quantize to that. You want to snap to grid when there is an underlying grid, like there is in language. Mm-hmm. Otherwise, you're wasting representation power.
Yeah, and so like they're trying to use diffusion for language, and they're trying to use LLMs for images, and we'll see, what happens, because maybe it's just fun. Maybe there isn't that same fundamental unit that we have with words, So nobody's sure that this is going to work. But anyway, but that is the thesis for this VAR paper, is LLMs work really great and scale really great.
Mm-hmm.
So is there a way I can transform the problem I want, which is generating images, into that shape of discrete predict next token, okay, and see whether or not it then kicks butt and does really, really well on this problem, right? It's like, I remember being in college, and right, it's like, oh, I'm trying to solve this, I don't know, whatever, truck routing problem, and they're like, oh, actually you can transform this into max flow, and we have an algorithm for max flow, so voila, that's all you have to do is transform your problem and then solve it as a max flow and then untransform it back into your original shape, right? So that's basically the idea they're saying. Nobody's saying for sure this will work, but that's the thesis as to why, the motivation behind trying to do this paper.
Rolling back to that, my original question. So I can kind of pretty quickly and intuitively understand the example, with the units circle or sphere.
Yeah.
I'm wondering how that works. In high dimensional, almost everything's almost perpendicular and everything's the same distance away from everything, right? So I'm just wondering how, I guess I'm struggling a little bit with how do you find the buckets?
So,
or does it just work? You apply the same math and it just works at higher dimensions?
It can work to a certain degree, because even though we say almost, it still is true that one vector will be a little bit closer than another one.
Yeah.
Right? They might be almost orthogonal, so like the dot product might be, 0.001, but for something else it might be 0.002, or something else might be 0.0001, and then you still have better and worse, right? But it turns out that, in fact, you're right. They don't train the VQ-VAE based on how they don't directly train it on how well did the bucketing work. Okay, What they actually train it on is the image reconstruction largely.
Okay.
Okay. And then you're like, if you had evenly spaced buckets, but it turns out all your data points are east, okay, then what's going to happen is all of your images are going to get maps to the same bucket, and you're not going to be able to separate them from each other. So then when you run it through the decoder and you generate images, you're going to get a whole bunch of whatever, right? So let's say you started with dogs and cats and airplanes, and if all you get is a bunch of dogs out of the decoder, when you do the image reconstruction loss, it's going to be huge. And so when you backpropagate through the vector quantizer, shifting the buckets around so that you actually have more buckets so that you can separate the airplanes from the cats and from the dogs, that will help your reconstruction loss tremendously.
Yeah. Okay.
And so it's actually done indirectly. You're absolutely right. They don't just only train the vector quantizer based on bucket spacing.
Okay. And is that kind of, how do you adjust the buckets? Is that kind of a gradient descent type of approach that there's
yeah, you can literally just say the L2 loss and then just run gradient descent, and it will work. It'll spread out your buckets to match your data distribution. Now in the VAR paper, if I remember right, they had 4 losses, and the biggest one was the image reconstruction loss. Okay, they did actually have, I believe, a loss component, if I remember right, for the rounding error, the L2 loss on the rounding error caused by the vector quantizer. So they did have it explicitly in there, but I don't think that was the biggest loss component. The image reconstruction loss was the main loss.
Heaviest weight. Okay.
Yeah.
Great. Thank you. Thank you, Ted.
Yeah. Cool questions. Another one. Yeah. Frankie.
Oh, sorry, Ted. I was just going to comment. I think the impression I got from the questions was that, why don't you just leave it in continuous space? Well, reality is that you're always quantizing anyway, right? Because you have a certain precision on your floating point units. So you're already quantizing it. You just don't know it, but you're quantizing it. Now, why further quantize is because you have limited resources. So therefore, your compression is kind of like how to best optimize my resources. For example, if I have 1,000 code book, that's much easier to keep this high dimensional space. So then I can better use those resources to do other things, like how are these codes related to each other, right? That's how I should spend my energy in my training, not necessarily in expanding as much as I can on this high dimensional space. So I look at it as more of a saving of resources in some sense to do, yeah. Sorry.
Yeah, that's a great comment. Thanks for sharing that. Yeah, obviously going from a 16 by 16, so 256 plus 3 color channels. So going from like a length 768 vector to a single integer, that's a heck of a lot of compression. All right, let's keep going, and these questions are great. We'll see if these questions feel like they're getting answered later on, or maybe they're not, and we need to revisit.
Gaussian distribution shown in the diagram. So now what we're going to do is instead we're just going to have buckets that we assign things to, and the common terminology for the list of buckets is our code book. All right, one second. There's a question. Let me just check this. All right. So you got it. So the code book is going to become the vocabulary for our LLM. And in this case, when you build a VAE, you pick the code book size in advance. You pick how many buckets you're going to have, which is pretty much what we do with our LLMs, is we pick, am I going to have a 30,000 vocabulary, a 50,000, 100,000? And so this is the way in which we will now take our embedding and we will discretize it so that we could use our familiar GPT-2 architecture in order to do predictions. All right, so this is just a little side comment on dimensionality reduction and discretization. So then we still have to kind of finalize, how do I take an image and shove it into, have different scales and shove it into here, okay? So the top bullet, VQ-VAE, it'll embed an image, but we're not quite all the way there, okay? So the solution that they came up with in this paper is we're going to break the image into patches, but we're going to give low-res images fewer patches, and we're going to give high-res images more patches, okay? And it's probably easier if I just explain exactly how it did it rather than the theoretical concept, okay? So basically what they do is they take the image, they run it through CNN, and they get a 16 by 16, and I don't know what the other dimension was, but 16 by 16 by some number of channels representation at the CNN bottleneck, okay? And when they want the super low res one, what they literally do is they just call the PyTorch, the linear algebra interpolate function, and they shrink it down to a 1 by 1, which basically means they just get the average of all 256 pixels. And so they say, this one average, I'm going to run through the vector quantizer, and that's the sole representation of the entire image. Next higher is going to be a 2 by 2. So I'm just going to call like the PyTorch equivalent of CV2 resize and say, here's my 16 by 16, resize it to 2 by 2. And then I'll run each of those 4 into my vector quantizer. And then for the next higher resolution, I do 33. So we do 1, 2, 3, 4, 5, 6, 8, 10, 13, 16, or whatever. And the final one is the full 16 by 16. So that one gets 256 patches to fully represent the image. By the way, these were ImageNet images. So this was trained on a relatively small problem. This is not trained on super high res. So these are, I believe, 256 by 256 color images for whatever, 1,000 classes for ImageNet.
Can I ask a very quick question?
She.
So what you described as the ground truth while training, it's like what you showed before, it goes from small to big and then it gets the whole image. What you just described, is it like the ground truth, or is it like how you train back the entire, like, I just don't get what it is exactly.
Yeah, so the question is like, what's the ground truth and stuff? And I haven't really explained that. What I'm saying though is that our different resolutions, how we will represent them as data, is that the lowest resolution is going to get one single vector, which will be represented by our VQ-VAE single codebook number. So literally, if our codebook is, I don't remember what the size is, but let's just say it's size 16,000, then the lowest resolution is going to be an integer between 1 and 16,000 that just represents the bucket that was the closest to our shrunken representation. And then the 2 by 2 is just going to be 4 integers, and so on and so forth. How we train this and everything, I haven't said yet, but that's what the actual representation means. So one of the questions is each resolution going to have their own codebook? Intuitively, you might want different code books, but and I've seen other people talking about this paper and asking that same question. It's a really good question. However, the purpose, where we're headed, we haven't talked about it yet, but where we're headed is that we want our transformer to take resolution 2 and predict resolution 3, the next slightly higher resolution, okay? And we would then want it to take resolution 3 and predict resolution 4, and so on and so forth. What that means is that every resolution must have the same vocabulary. That's the way LLMs work. You can't change vocabulary halfway through your text where somebody asks a question and they say, you know, what is the tallest mountain? And then you just change your vocabulary. No, it has to be one vocabulary over all time. So what we're going to do is we're going to say each patch is using a shared vocabulary, but low res gets 1 patch. Next res gets 4 patches. Next gets 9. Next gets 16, and so on and so forth until the final one gets 256 patches, and it can therefore have a lot more information content packed into it. We're still going to have a decoder that interprets those patches. So we're not saying that these patches are literally just pixel values. Okay, the embedding into these patches can be anything that the model wants to do, but we're just capping the amount of information that's available to each individual resolution. Question, Tony?
Yeah, so you mentioned resolution, and he had the question resolution. So we were wondering, are either of these factors the reason why stable diffusion, for example, a lot of the libraries have been trained to generate at 512 by 512 and work fairly well. But if you change it to 512 by 768, you get a lot more fingers, for example.
So the question was about like stable diffusion and changing from 512 to 512 to 512 by 768. Honestly, I don't know the answer to that. We can have a conversation about how the diffusion models work, but I'm not really sure about that. Okay, so second bullet here, we're going to need a special VQ-VAE. We can't just use a vanilla one. We need a special one that's going to understand different resolutions. And what we just talked about is like that the decoder is going to be able to make good sense of the high res images as well as make sense of the low res images. So then finally we get to the LLM part. Okay, so our LLM, it's supposed to predict the next higher resolution given actually not just the previous one but all the previous ones. So if you're trying to predict resolution 5, you have access to resolution 1 and 2 and 3 and 4. Okay. So as I mentioned in the preview, GPT-2 predicts 1 token at a time. So the input always grows 1 token at a time. If you've ever seen one of those autoregressive mask diagrams, you see it kind of looks like a triangle. It's just got kind of a straight diagonal. Pet peeve, I actually hate the way people make those mask diagrams because for whatever reason, people never label the axes and say which is the query and which is the keys, or even the fact that you're supposed to know that queries and keys are the 2 axes, but they never say which is which, and they never say which is the lower end and which is the higher end. And you're just supposed to like magically know this. So for a bunch of like, data scientists, we've like, in those diagrams, we've really like violated like the first 3 rules of how to make a chart. So, but nevertheless, if you've seen one of those, ours is no longer going to just be this nice triangle. It's going to have these chunks because we're going to have 1, and it's going to be what the 4 pixels that you're predicting all get to look at. And then when you're predicting 9 pixels, they don't get to look at each other, but they get to look at the 4 and the 1. And then when you're predicting 16 pixels, the last of this, because ultimately we'd still have to write them out sequentially, okay? But we're going to create a mask so that the 16th pixel doesn't get to see any of the 15 that came before it. It's only going to get to look at the 9, the 4, and the 1, okay? So we're going to have a funky looking mask. And then that basically will let us sort of reuse GPT-2 as is, but predict in chunks where, again, there's no extra information that later pixels at a certain resolution have an advantage over the earlier pixels you output. Yeah, so it seems like a sliding window, but in this case, the way we're sliding the window is we're sliding it not uniformly, but we'll slide it 4, then we'll slide it 9, then we'll slide it 16, then we'll slide. That's a nice analogy. Okay, so ultimately, what is built is this multi-scale VQ-VAE,
Yeah, Jerry, you want to pause?
And
Ted, the examples that you're using sound like they were integers squared. Do the resolutions increase like 1 at a time, or do they kind of double in both dimensions at each layer?
So ultimately, that's just an implementation detail. It turns out that they went from 1 by 1 to 16 by 16 because ImageNet is square, right?
Yeah.
And they wanted to run a little faster, and they were able to get away with going from 1 to 16 in 10 steps. So they went like 1, 2, 3, 4, 5, 6, 8, 10, 13. They skipped some numbers, okay? But had they just gone in 16 steps the concept would be identical. It just would have run whatever 20% slower because they would have done a few extra inference steps.
Okay, but they're using the same you said same code book, same model essentially at each level, going from one level to the next.
Yeah, and what's now on the screen, this multi-scale VQ-VAE is going to be important. And what we'll see is that this is actually trained separately from the LLM. So this is an autoencoder. Okay, it's a very weird autoencoder because it does 16 levels of resolution instead of just doing it in one fell swoop. But it's an autoencoder, and so it does reconstruction. It has an encoder and has a decoder, and it'll do its thing, on its own, independent of the LLM. But then what you have the LLM do is you have it then predict the next resolution without actually having it.
Okay. Okay.
Yeah, Frankie?
Hey, Ted. I just want to, something that I struggled a lot on this paper was that the fact that they're using LLMs. And I kind of thought about, like, why does it work? And I wanted to go by to your understanding, make sure it's correct. So, when we think of LLMs, right, we're putting a prompt and getting the next token prediction. And it seems to be very free form, right? That is, I can put an arbitrary prompt and I can get like arbitrary length response, right? And so when I looked at this paper, it's going, if that's the case, how can you apply the same thing to this? Because, obviously they're applying resolution 1 and then get resolution, I'll just enumerate like the next resolution 1, 2, 3, 4. And then if after you put 1 and 1, 2, 3, 4, then you got to get 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So how I struggled with that is to say, we have a very special language in some sense, which is very structured. That is, I'm feeding a very special set of tokens in training so that I always get this special like sequencing, resolution 1, resolution 2, resolution 3, and they all have that particular size. So the way that I thought about it is that, okay, well, even LLMs have an end of text token, right? The LLM knows when something finishes. But in this case, I have a very structured language, if you like, of these resolutions. So therefore, I don't have to struggle with the fact that it will give you 4 next tokens. It will give you 9 next tokens. It will give you 16 next tokens given the conditioning. So that's what I want to make sure. That's my understanding. It's like that's how I trained it. It's a very special type of language, and therefore it's going to spit out exactly that kind of sentence coming back. Is that okay? Yeah.
You're correct. This is a very special language. And so anytime you give it 1 plus 4 plus 9, so you give it 14, inputs, it's always predicting 16 next. Right. But the reality is they made life even easier. It does not actually even need to do an end of sequence. They could have implemented it that way, and I think it would have worked pretty well. Okay, but that would have required 16 passes through the decoding. And so for the purpose of speed, what they do is they give it the prompt, as it were, which is the 1 plus the 4 plus the 9. And then they give it a set of 16, I'll say dummy, but don't take the word dummy too literally. 16 dummy input tokens, and then they predict all 16 of those simultaneously. And then the model doesn't even have to worry about outputting an end of whatever sequence token, because you do one decoding step, and even if it wanted to do a 17th thing, you just turn it off, and it has no chance to give you anything else.
I did notice that the one that you talk about this. Suppose we're going from 1, 4, and to the 9, right? I did notice that they're doing this interpolation. The dimension that you said, you're adding the 9 inputs, if you like, but you're asking to predict the 9. They are doing some kind of interpolation at level 2 to level 3 to have this stuff, which I thought was interesting. I'm not sure it's necessary, but I guess that helped them in maybe because they're doing what do they call that? Yeah, sorry.
They wanted it to be fast, so there was no way they were going to do it one at a time. They were always going to do them in parallel.
And
so just figuring out how to set it up.
Yeah, I was just going to say maybe it feels like a gradient boosting technique too, because you're always giving the delta. They're training on the delta. You give the interpolation is kind of like the closest that you can get. You're then predicting the delta to the next level, right?
We haven't gotten to that detail yet,
sorry.
but yes,
Okay.
it is going to be just like gradient boosting.
Okay.
Yeah, Julius?
Is it fair to say that the dummy tokens, first one, then 4, then 9, then 16, can they effectively serve as kind of a scale encoding? So we have temporal encoding and transform. In other words, it's telling the network what size it's working on. Is it fair to think of it as being the clue that it needs to know that it's working on that scale?
It's a really good question, and I actually at this point don't remember all the details, how they encoded position and scale and whatnot. But intuitively, okay, we're all saying the same thing. That basically, there's another detail. So this is ImageNet, and so you get to actually tell it what class you want. I want a dog. I want a plane. I want a rose. Okay, so there's actually an extra class token that's at the very first input. Okay, so technically speaking, so class plus 1 plus 4 plus 9 is 15. Okay. So when the model has a prompt, as it were, that's length 15, it always knows that it's outputting a 4x4. And when the prompt is length whatever, 31, it knows it's outputting a 5x5. And so, yeah, I don't remember exactly the details of how the position and scale were encoded, but it always looked like that. There's no variability to it. Every time my prompt is this length, this is exactly what I'm predicting. And so, yes, it gets hardwired in as part of the training. There's no way you could zero shot this behavior using Llama 3. No, this is very much trained from scratch for this one specific problem, and it can only do this problem. It could never do anything else along the lines of what you're saying.
Baked in at training. Yeah. Thank you.
All right, Jerry, I don't know about time.
Yeah, we're kind of close. You obviously know what's coming better. Will you have something that we can wrap up in 5 minutes, or?
So let's actually do the VQ-VAE, which means we won't get to the LLM part, but I think this will help encapsulate the stuff that we've been talking about so far.
All right, I'm going to start it up.
As was mentioned, all the scales, embeddings, they're using the same code book. It's just you get more patches for the higher level ones. I believe from the paper they said they tried this where they just built, the 1x1, the 2x2, the 3x3, the 4x4. Ultimately, what worked better is they said the 2x2 is not the full image, but rather the delta of the full image minus the 1x1's information. Okay, so if you take the 1x1 and you just spread it out, and then you subtract that. And so if you're familiar with like Whisper, many of these other audio models, they all use residual vector quantization, where they vector quantize and then they subtract that from the raw audio signal. And then from that delta that's remaining, they vector quantize. And then when they have that, they subtract that. And then and usually it's like about 4 times that you do vector quantization. And in that case, I think it's because like the amplitude of high frequency and low frequency signals in audio is different. And so I think early vector quantization tends to get low frequency data, and then later ones tend to get high. And maybe there's something similar in images or not or whatever. But essentially that's what's happening is instead of just saying we have these different resolutions that are copies of each other, as it were, each successive higher resolution is just representing the delta of whatever the previous resolutions missed. And so when you want to reconstruct the image, you actually sum up all of your resolutions, and then you send that to the decoder based on that. So I'm obviously skipping some of the details, but I'm just going to keep going here. So not going to go through here, but if you look at the algorithm that's in the paper, basically what you're going to see is they're going to say for 1 to k, in this case, k was 10, okay? They, like I said, they start 1, 2, 3, 4, 5, 6, and then they skip some numbers and they get up to 16 by 16. But you're going to start with your 1 by 1, and then later on, when you build your 2 by 2, you have to already have had the 1 by 1 because you're subtracting that from your raw image. And then you subtract the 2 by 2 from that result, and you keep subtracting and subtracting. And so if you think about like XGBoost or something like that, this is sort of a similar operation where you just keep trying to refine on whatever you missed in your earlier steps. So the training is,
all right,
you
so
train
let's
the
pause here,
multi-scale
Jerry.
VQ-VAE.
And if you don't mind going back to the previous slide, you just go back one. Yeah, perfect. So just a little bit of additional color. So what happens is on the left, it's the algorithm for encoding. And so what it does is it takes the 16 by, it takes the full image and scales it down by a factor of 16. And it runs that one patch through the vector quantizer, and it ends up with a codebook value. So the codebook in this model was 4096. So you get an integer between 1 and 4096, or if it's 0, index between 0 and 4095, whatever. You just get one integer. And then what you'll notice if you look at this algorithm, don't have to go through all the details, but there's this Q push thing, okay? So basically it's saying, let me store the output from the 1 by 1 resolution. Now what I'm doing is I'm taking whatever that 1 by 1 predicted as being the full original ImageNet image, subtracting that from all the pixels and saying, this is now my residual, this is what's left over for the next one to predict, okay? So that's line 9 there, where you see F minus whatever the first level predicted. Now we're gonna resize this down by a factor of 8, and we're going to run it through the quantizer 4 times, because it's a 2 by 2. And so we're going to end up with 4 integers, and we're going to push those onto the queue, and so on. So we repeat this until finally we have the 16 by 16, where there's the original pixels, and we're not going to resize it all. We're going to run it through the vector quantizer 256 times. We're going to end up with 256 integers. We'll push those onto the queue, and now we'll be done. Now we'll have the whole thing. On the right, they show the reconstruction, and you're going to see we have the same loop, okay? So what happens is you take the original single integer, you look it up in your code book, and you get that, buckets, whatever, centroid or whatever, and you use that for reconstructing the full 256 by 256 pixel image. And then you get the next one, and you project that, and you sum that up, and now your image is going to look a little better. And then you get your 9 integers, you run those through, you add that, and you do this until the 16 by 16. This is how you would work with the VQ-VAE all by itself. Okay. What happens is when we're in image generation mode, what we're going to do is let's say we already have the 1 by 1, okay, and we have this like very basic image. The next step here would be pop the 4 integers from the 2 by 2 off the queue in order to reconstruct. But we don't have a queue when we're in generation mode. What we have instead is an LLM, and the LLM is going to predict the 4 integers just based on the information we gave it from 1 by 1. And it might predict well, it might predict badly, and then we're going to basically sum that up as part of our image reconstruction. And then we're going to say, hey, LLM, I have now 5 integers for you, the 1 by 1 and the 2 by 2. Predict the next 9 integers for me for the 3 by 3, and then it can take that, run that through the decoder part, right? And so So if we were doing just VQ-VAE, you run algorithm 1 and you build up this queue, and you run algorithm 2 where you're popping them off and you're reconstructing the image. And at the very end, line 10 on the right, you have reconstructed image hat. Okay, and now you can calculate all your losses to see how good a job did it do of reconstructing the image. When we're doing generation, instead of QPOP on line 5, we say call LLM to predict what the next thing coming off the queue would have been based on what we've already seen. That's the whole point of this paper, is to use an LLM to predict the non-existent, because we're generating, we don't actually have an original image that we encoded. We're just saying, generate a dog for me. And so the LLM is saying, if all I know is that you want a dog, I'm going to predict this sequence of 1 integer and then 2 by 2, and 3, 4, and so on until I predict the final 16 by 16 grid of integers. And hopefully when you run that through the decoder, you'll get something that looks like a dog.
Is there any sampling here, or is it fully deterministic? In other words, are you just resynthesizing the image using the centers of the buckets, or is there somewhere some randomness?
I'm like about 99% sure that the VQ-VAE decoder is completely deterministic, but they do temperature sampling on the LLM, on the GPT-2.
Okay, so you do you've got a logit distribution there.
Yes.
Yeah.
So if they did 0 temperature sampling of the LLM, then you would get the exact same dog every time. But because they don't, then by chance you'll wind up with different dogs.
And even when you jump to another logit, you'll be jumping to another bucket center, right? So you're never really doing a mean and standard deviation interpretation of the bucket value.
Right. Yes. And then
that's interesting.
And then the same way that I think about language. So if somebody asked you, what is the capital of France? Okay. An obvious completion would be the capital of France is Paris. Okay. But if somehow you were temperature sampling, you were doing some kind of sampling, and you messed up, okay, and you somehow said the biggest city, like now you're kind of in trouble because that's not what the user asked for. They asked for what was the capital. But in theory, if you saw in your context of an actual language model, what is the capital of France, the biggest city, and you said predict the next few tokens, you might correct yourself and just say like, I will say, and also the capital is Paris. So you can correct from that mistake, okay? Mm-hmm. And so if you're doing image generation and you do sampling and it's like, this is supposed to be a German Shepherd, and then you just like picked a red, codebook entry that somehow wound up with a bunch of red pixels, then you're like, I'm going to twist the image a little bit so that the dog's mouth is there and their tongue is sticking out, and that's where the red pixels are going to line up with, right? Or I'm going to have the dog be in front of behind a rose bush, or I'm going to have a kid standing next to the dog with a red balloon. But like that's how you can like correct from a mistake at an earlier step, right? So the beauty is if you have a really good language understanding and for some reason you just said the wrong thing, the biggest city, like, well, shoot. But there is a way to circle around and correct for it. And I think in the image space, there's the same thing where it's like, yeah, you'd expect there's sort of a canonical, whatever, German Shepherd picture. But if you did predict something weird, then you're just like, oh, I need red. I'm going to have a rose bush next to it. I need blue. I'm going to have the dog next to a pool. There's just ways that you can say, like, this is still internally consistent with my world model. I'm conditioning on what I do know, and I'm making the most sensible German Shepherd picture of this low resolution thing that has mandated there must be something red or blue in this one particular spot. And so that's why, in my mind, that's why this conditional generation works. That's why diffusion works. Diffusion, you can take a random step in a terrible direction, but in future steps, you can pull yourself back towards the center of the distribution, something that makes more sense. It's the same thing with next token generation. It's the same thing in my mind here, where as you go from low to high res, even some really, it's like improv, right? The other person says something to throw you off, and you just your job is to have it work.
Makes sense. Yeah. Do diffusion models operate at multiple scale? I don't know much about diffusion, but it doesn't seem like they really change scale. It seems like there's more noise or less noise.
The noise scale reduces. So in that sense, they are similarly going from coarse low res towards higher res. Because when your noise scale gets really low, you cannot correct for the fact that there's a giant bunch of red pixels on the dog's left leg. It's too late. You can't do that. Early on the process, when the noise scale is really high, then you can just be like, guess what? There was a rose bush in front of the dog's leg. Ta-da! Solved my problem. But once the noise is really low, all you're really doing is adjusting like the fur pattern. You cannot make any big changes at that point. So that's how I feel like it is. It is sort of doing a similar kind of thing.
Has to resort to fire ants on the poor dog.
Yeah. But something like if you torture it enough, it will still find the closest thing that it can that's in distribution.
Torture the model or the dog?
The distribution.
Okay. The dog distribution.
Find the tails.
Yes.
The tails of the dog.
Pin the tail on the dog.
And the tail of the distribution. Sorry.
So next week we can go into a little bit more about exactly a few more of the details, but I think now we have a picture, hopefully, a picture of what the authors of this paper really were going after. They said, I wanted to do something with LLMs as is, where it's discrete input, discrete output, next token prediction. And I wanted something that was more intuitive than a raster scan or some other spiral pattern. And so I'm going to do next scale. How do you represent scale? And ultimately what they came up with is, I can't represent next scale with uniform one token at a time. The rule I need to break is I'm going to predict multiple tokens at a time. First 4, then 9, then 16, all the way up to, in the last step, I'm going to predict 256 tokens. All at the same time, conditioned on a prompt that's, I don't even know what, 4 + 9 + 16 + whatever, but it's like 700 tokens long or something, whatever. It's 1,000. It's pretty long, right? And I'm going to use GPT-2 right here in that step number 5, where I have no encoder. This was a purely from scratch generated image. So I'm replacing QPOP with, hey, had this been a real image that had been encoded, GPT-2 predict for me what the next 4 codebook integers would have been that popped off the queue, based on everything you know about images and all of the lower res integers you've seen so far. And so, so Julius, like you said, it's a very special language. It's not English, it's not French, but this is a particular image ease language that they trained it on.
And it's still going one token at a time. It's just that it knows it's got a window of 16 that it's got to produce, and it's been given that room in the input buffer with the dummy token so that it just fills that in. That's
mathematically
beautiful.
The results would be identical whether you output them one at a time with a mask, so that the first 15, none of them can see each other or whatever, or if you do them all simultaneously. For the purpose of speed, they did them simultaneously. They did not do them one at a time.
Mm-hmm.
Yeah.
Cool. Thank you so much.
Oh, I had just one thought. I just had one question. Quick question. So,
yeah, please.
When we're looking at, let's say, the 16 by 16 256 tokens being generated, and we're we're trying to see like what are they attending to in like the previous squares. Do you think that there's not really much information in like 1x1 and 2x2, etc., and most of the information lies in just the previous square that was generated?
If they had chosen all the resolutions to represent the actual image, then my guess is exactly what you're saying, that it would mostly just attend to the next best resolution. Okay. Since each subsequent resolution, as it gets higher res, is actually only representing the residual, it is forced to also look at the lower resolution ones a lot. Because the lower ones are going to say, like the first 3 or 4 are going to determine that the bottom quarter of the image is mostly green, the top quarter is mostly blue, the middle's mostly brown, you know. That will not be available in the second highest resolution, because that second highest resolution is only the deltas, only the corrections from the previous set of predictions.
Got it. Thank
So
you.
in the end, I'm not surprised that it works better, because what you kind of want is you want it attending to everything that it's seen, if it can do so, if it's powerful enough. So if instead of using GPT-2, you used whatever, some teeny LLM that has only 6 layers and only has 10 million parameters, right? It's probably not powerful enough to attend to all, like, you know, whatever, 1,000 odd tokens by the time you get to the last round. So it does need to be a powerful enough LLM. But ultimately, then yes, the way they constructed it, they're really forcing it to do that. And you could argue to a certain extent, it needs to sort of actually compute the running sum from all of those things in its internals in order to make a good next prediction.
Right.
Thanks for the question.
Thank you.
All right, so Jerry, I think we'll stop here, and don't know if we'll need the full time to finish, because hopefully at least we've got the big concept, but we can spend a little bit of time talking about, there's other papers. I started to look at that XAR paper that is also from ByteDance, and it has some complicated wrinkles. It's not just changing the attention pattern, and so I'm not even sure if I'll be prepared to speak to it, because it's kind of gnarly.